Okay, so once again, I'm very sorry, apologies for the delay. So my name is Laurent Montes, and I would like to present you some slides about what we're doing from MEMS to NAMS, from design to characterization, from fundamentals to applications, within MECHATRONICS Innovation Center, which is just 3 hours drive when you don't have any car problem from here in Grenoble. And as expected by many scientists, there is different convergences within the, let's say, standard microelectronic area, what we call Moore reduction law, consisting mainly in reducing transistors. Another point of view is to introduce on the same chip more and more technologies, so basically MEMS, and also, why not, what we call beyond Moore technologies, so typically nanotechnology. So what we tried to do within this MECHATRONICS Innovation Center is to work in synergy to make all those devices work within one single chip, whether it is a system on chip or system in package. So it's a quite new research center. The driving force is that we have both education, research, and industrial development nearby, together with some informational resource building center for conferences and so on. What we work in is, first of all, design and simulation with both industrial tools, but also proprietary tools, such as demo you have here. This is a nanowire heterostructure nanowire under stress, typically 1 gigapascal stress, and we look at how the formation is, and mostly we want to integrate this kind of nanowire heterostructure within a device to make, for instance, a pressure sensor. So we have different kind of tools, and I think the main specificity is that we can develop our own code on those one and make the application we'll see later on of this amplifier, for instance. So we also have some technological resources in different platforms. One that is pre-industrial fab, so 300 millimeter microelectronic fab, another one devoted to MEMS, and other mostly devoted to research and prototyping. We have some research capabilities from, let's say, a biotech to nano world, so making those kind of nanowires. You don't have the scale here, but it's in the range of 20 to 40 micron in size for typical devices that we can produce, together with, let's say, standard IC design and manufacturing, and all together with radio frequency and microsystems. We have now running up very recently some new tools, including very performant tools such as e-beam system and so on, devoted not only to nanotechnology but also to microsystems, and try to make those two technologies, let's say, work all together. And this all along, so these research facilities, all together with industrial prototyping line to make sure that, in fact, everything we do can be industrialized later on. We also have, together with those tools, nanocharacterization platforms, electrical platforms, like you can see on the backside of the image, so nanomanipulators, cryogenic systems. The one you have here can hold 300 millimeter wafers down to 4 Kelvin and make measurements up to 100 gigahertz, and all together with microscope like the Titan II, so very powerful microscopes. Okay, so this I already said. And some examples of what we've been doing lately. So for instance, here we have a microelectronic device that is in fact a microcooler. So the lines you have here are in fact microchannels. You can see them just because it's in infrared. If not, it's on the back side of the substrate. And the very small square you have with enhancement on the right side of the picture, those are the pressure sensors that we have integrated within. And the goal was just to make sure that the design and simulation we had on microscopic fluidics was working still at this kind of scale, which is in the range of hundreds of and even lower microns. So this is typical pressure sensors that we make. So the very specificity of this one is the thickness of the membrane that is very extremely thin, much lower than 1 micron thick, and such very sensible. If not concerning really what could be called as nanomechanics, we are now developing more in research mostly, but going to industry now. NEMS or nanowires and nanotubes. So on the left side you can see a nanowire, and looked with an atomic microscope and looking at how vibration goes along the wire, or nanomanipulation on the right side, see how this spaghetti, which is a nanotube, we can just force it at the very edge, and then because of the accumulation of energy, will just jump on top of the contact. We are also making NEMS with diamond to look for quantum fluctuation in those NEMS, to see if quantum quantization exists also in the mechanics. And making nanoradios, so this is with a large industry group to look if there is any capabilities to introduce this in your future cell phone, for instance. We can manipulate the nanowires, nanotubes, nano objects, whatsoever, also just by touching. So we have developed a nanoforce sensor with a feedback control, so that you can really sense and not only use a computer to manipulate those objects. And not only we do it in research, we also have education based on this, but this I will talk later on. And finally, we have some technological transfer. For instance, we have a new startup just created working on how to integrate those technologies. In this specific case, it's for integrating micropumps for biomedical implications. The picture you have on the bottom here is a syringe that works using this very secure micropump and sensors integrated. And I would like to thank you all for your attention, and especially Mr. Chairman. And thanks also for the organizer for inviting me. And if you have any question, we can talk later on. Thank you.